Hello, everyone. I hope you can see my screen. Deep Learning with Python. My name is Dimitris, and this will be chapter 8 of the book. So, introduction to deep learning for computer vision. More or less what the title says. We will go through the introductory things regarding computer vision, and in the next chapter, we will go a bit more in depth. So, in this chapter, we will see the convolution networks, which is the dominant paradigm for computer vision with deep learning. We will try to understand how convolution layer works, how max pooling works. We will also see data augmentation, so image augmentation, in order to mitigate overfitting to our training. And we will also see how we can make use of pre-trained models, either for feature extraction or for fine-tuning, in order to increase the performance of our models. So let's get started. First of all, it's worth mentioning that computer vision is the earliest and the biggest success story of deep learning. And it led to the initial rise of deep learning between 2011 and 2015. And it was actually in 2012 that Hinton's group won the ImageNet challenge. So ImageNet is a high-profile, large-scale visual recognition challenge. And the idea is that the results of Hinton's group on 2012 were so different than all the previous years that it immediately got the curiosity of the researchers. They started looking to what is this new technique that got so good results, and in the next couple of years it started becoming the dominant paradigm, as I mentioned before, to challenges, to applications for computer vision, for everything. So let's start with the introduction to convnet. So we will start in a quite curious way. We will first use them and then explain them. So we will first run an example that we have already seen before using convnet, and then we will get in more detail on what is this thing that we used. So first of all, we will create a model. So we import kernels and layer, and we will use this functional API in order to construct the model. From now on, we will mostly use functional API. We have already seen in the previous session. So we create an input layer, and then we have blocks of convolution layers and max pooling. Again, we will explain in more detail what these are in the next slides. So 2 and 3, this is the third convolution layer, and then we have flatten, and we use the dense layer with 10 outputs as a classifier. Since we will run it on MNIST, we will have 10 outputs with softmax activation. And this is the way we build the model, so inputs and outputs. Let's run this one and continue to see the summary. So let's display the summary of this model so that we can gain information regarding the layers. As you can see here, we have what I described before, an input layer with 28 by 28 by 1 as dimensionality. Be careful here, since we use convolution network and convolution layer afterwards, we have to input a tensor with rank 4. So the first dimension, again, is the bat dimension. So it's actually rank 3 tensors. And these 3 ranks is the width, the height, and the number of channels. And this is what the convolution 2D expects as input. And here you can see that we have 26. From 28, we drop to 26. We will explain why. 32 is the number of filters that we defined for the first convolution. And then we have max pooling. Again, pay attention here that we have half of the height and the width from the previous layer after the max pooling. We keep the same number of filters of feature maps. And in the next convolution, again, the previous -2, and we have 64 now, and then 128. In the end, we flatten it. So this is a number that we take by multiplying 3 by 3 by 128. And the output is 10 numbers as explained before. So we have around 100,000 parameters. Remember this number because we will see a differentiation later on that we will have much more parameters. So around 100,000. Now, let's load the MNIST data. We have already seen this. We import MNIST.load data. We get these tables with the training and the test images and labels. Now, one thing that is different than what we did before, if you remember before, we reshaped to 60,000 the first dimension, and the second one was 28 times 28, so one dimension. Here we have 28, 28, 1. So the difference is that we add one channel, and this is because, as I explained before, we want 3 channels as input. So if we don't have, we import one dummy channel for grayscale. This is exactly what we did before. So we divide by 255 the images so that we are in the range 0 to 1, and we apply the same thing on test images. We will compile using RMS probe, sparse categorical cross entropy, and using accuracy, so nothing new here. And we will fit it for 5 epochs with batch size 64. So if you remember, during training, we had run the exact same dataset when we used at the chapter 2, I think, the dense layers. So we had a bunch of dense layers, we had this network, and we had some test accuracy around 97.8%. And now we will see that we will get much better accuracy. And this is the difference with this kind of convolution networks. So let's see what will be the evaluating results. And here you can see that from 97.8, we are up to 99.2 and can get even higher actually. And if you think that, okay, from 97.8, just 99.2, so it's 1 point something, it's actually much bigger, the difference, because you have to think what is left. So if you think how much we reduce the error from previous time, it's more than 61%, the difference between the 97.8 and the 99.2. Again, remember, you have to compute the difference, what you miss, to see how better it got. Now, let's continue and explain what we just did. So we built a model with a bunch of convolution layers and max pool layers, but we didn't actually explain what this is. Let's see what is the convolution operation. So we should, by this point, be quite familiar with dense layers and how they work. And the idea with dense layers is that all the information, all the 28 by 28 pixels, pass the information to the next layer. So the dense layers have access to the global patterns. They learn from the global patterns in the input feature space. But the convolutional layers actually learn local patterns. And the way they work is that they have these things, these kernels, that they scan the input image. And they, let's say that we have this kind of square as a kernel, and this square will scan all the possible position of the image, and it will see only a small size of the image, a small portion. So the idea is that this convolution layer will learn local patterns. So at the beginning, it will have access only to small areas where it will see what is the, if there are some curves, what kind of curves, what is the orientation, if there is some specific texture at the image, so this kind of information, and it will only have local information. Now, the idea behind this is that these patterns that the convolution layer learns are translation invariant, which means that if it learns to identify, for example, I don't know, a face at the bottom left corner, then it will be able to recognize the face also at the bottom right corner, which means that the position of the pattern that we are looking for is not important. And this is why we want something that is translation invariant. And we don't have this feature when we use dense layers. Another thing is that the convolution layers can learn spatial hierarchies of patterns. Now, what does this mean? This means that the visual world forms a spatial hierarchy of visual modules. Now, the elementary, at the bottom line, we have some like elementary lines or textures in like this example. For example, here you have the figure of the head of a cat. And this has some elementary lines, okay, or some elementary textures like this one. And then if you combine these elementary lines or textures into simple objects, then you can get something a bit more complicated, like eyes or ears or a nose. And then if you combine this even higher, you can get something like a cat head as an image. So the idea is that we start from very simple patterns or very simple elementary lines, and then we build on this and we build on this, and we have access to bigger portions of the image, of the original image, so that we can make more complex structures as patterns that we can recognize using this layer. So let's see in more detail how this will work, how we will have access to these patterns. First of all, as I mentioned before, the convolution operates over rank 3 tensors. So we have again the height, the width, and the number of channels. And these are called feature maps. So the convolution operation extracts patches from this input feature map and applies the same transformation to all the patches. So for example, if we have this image and we have this filter, then we will take this filter. This filter is just some numbers. And there is a fixed operation that is applied using these numbers and the patch numbers, the patch of the image. So we apply this to the same operation with the same numbers to every possible position of the image. And the output of this is what activates this feature. And this is why it's called feature map. So here we can see that this specific kernel, this specific filter, is activated mostly on this area and this area of the image. So probably it looks for something that has this kind of orientation as a line. And it's not activated at all at these areas and very few in this area, for example, or this area. So we have many of these filters, and each filter tries to identify specific patterns, like I mentioned before, this kind of orientation of lines or circular lines or some kind of other kind of patterns of texture. And for example, in MNIST, the first convolution layer will have us input this 28 by 28 by 1 image. And since we have 32 filters, 32 of these kernels, the output will be 26 by 26 by 32. So for each kernel, we will have one output feature map of the activation of this filter. Now we will explain why we don't have 28 and we have 26 in the next slides. I just want you to understand why we have 32, because we have 32 of these small 3 by 3 activation filters. Now, if you remember when I saw the model structure, at this conv2d layer, we have to define some things. So I didn't stay that long there, but we have to see in more details now what each of these parameters is. First of all, we have to define, not first of all, the kernel size is one of the parameters. So the kernel size shows what is the size of the path that is extracted from the inputs. For example, we used in most of them the 3 by 3. And 3 by 3 is quite common. In some cases, you might use 5 by 5, and there are cases that you use 1 by 1 for very specific reasons. But let's say this 3 by 3. The idea is that we take the window and the window height and width will be 3 pixels by 3 pixels of whatever is the input to this layer. Another parameter is the number of filters. So the number of filters, again, is the number of these kernels, these 3 by 3 matrices that we are going to use And this will be the number of channels that will be the output of this convolution layer. So this is how we define conv2d, and we have the number of filters, the output depth. And if we have, for example, 3 by 3, we will write here be 3 by 3, or we can write one number if it is the same. Now, the convolutions, as I mentioned before, slide the window over 3D input feature map and extract the paths and then apply the transformation output. And the output is 1D vector for each one of them. Let's see an example here. So let's say that we have this as input feature map. And we have something like 5 by 5 here with two channels, okay? And we extract from this volume the patches. So we want patches of 3 by 3, so we will extract 3 by 3 by 2, all the available volumes we have. And then we take this and we apply dot product with the kernel. And the output will be how many, it will be 1 by 1, and it will have as many kernels as we have for the number of channels. So each one of these patches will output 1 by 1. So for this patch, 1 by 1 by 3, because we have 3 output filters. For this patch, 1 by 1 by 3, and for this one, 1 by 1 by 3. And we have for each of these pixels, this 1 by 1 by 3. And then we get it back together, and the output will be, in this case, 3 by 3 by 3. Now, the output width and height, so the depth, the number of channels is what we define. Now, the width and the height might differ, as we see here, from the original one, for two reasons. One reason is the border effect. So we will explain in more detail what does this mean, but the idea is that in the borders, we have some specific way of treating it. And the other is the strides. So let's see what these things are. First of all, the border effect and the padding, what we can do in order to avoid it. As we saw before, we had a 5 by 5 input tensor by whatever, and then we had 3 by 3 window for the kernels. And this had an output of 3 by 3. So why is this? The idea is that for this pixel at the top left corner, we cannot apply this 3 by 3 window, right? Because there is no pixel here. So we cannot have this one as center. Neither this, neither this, neither any of these white squares. But this one has a 3 by 3 around it with this as a center, which means that we can take this one as well, this one, this one, this one. So the idea is that from this 5 by 5, we can extract these 9 patches. And this is why from 5 by 5, we drop to 3 by 3, because we remove the 1 left, 1 up, 1 right, and 1 bottom pixels. And this is because we have 3 by 3. If we had 5 by 5, it would remove 2, 2, 2, and 2. Now, the idea is that if we want to avoid this to reduce the size, we can pad it. We can use here, for example, zeros around the original input tensor. And using these zeros, we can take also, for example, this pixel, because now it will be the value of this pixel, this one, this one, this one, and we will have zeros around at the top and at the left side. And we can define this. So if you write padding at the convnet signature, then you can define either valid or same. If you define valid, it will be the behavior of this. So it will reduce a bit the input side. And this is the default value. If you define it as same, it will keep the same input. So if we have 5 by 5 as input, the output will also be 5 by 5 by padding with the zeros. Now, this is one of the reasons. The second reason that I mentioned was the strides. Now, let's see what is the stride. So here is an example of a 3 by 3 filter with stride 2. And the stride, the idea is that we skip some pixels. So instead of going and scanning the input tensor, each pixel of the tensor, we skip how many, we go to the next, this number. So instead of the next one, we go to the next 2. So from here, we will scan also this one, and this one. And this is why we will have in the end 4 of these patches. So the idea with Stride is that we can downsample the feature map if we use, for example, Stride 2 by factor of 2, both in width and in height. And although it's quite common in segmentation models, for example, it's not that common for classification models, and we will explain why. Now, apart from the convolution layer that I explained before, we had also the max pooling layer. So the role of the max pooling layer is that it will aggressively downsample the feature maps. So it's like the strides in the convolutions, but the idea is that it uses a fixed kernel that is the maximum. So whatever is the input, let's say we have a 2 by 2, which is the most common. So for every 2 by 2 area, it will keep the maximum value. And this will happen for all the 2 by 2 patches of the input tensor. So for each one of the channels, it will keep the maximum for each 2 by 2. And this means that it will reduce the width and the height by 2, a factor of 2. So in total, factor of 4, the volume. So this is a max pooling, again, just the maximum of the 4 values. Now, why we need this? Let's see an example where we don't use the max pooling to see why it's important to do this downsampling. So here we will build another model that will have the same input, the same convolution layers, but without the intermediate max pooling that we had after its convolution. Now let's see the summary, and here you can see that we have input, and then we have the conv2D, 3 of them, and then the flatten. Now what you can see here, first of all, is that we have something like 700,000 parameters, which is 7 times more or less more than what we had before. So this creates big models, and this is one of the negative ones. But the most negative one is that each one of these convolutional layers, even the last one, has access to a very small area of the original image. I mean, the first has at a 3 by 3, the second one at a, from the original image 5 by 5, the third one from the original image, the 28 by 28, at an area, a patch of 7 by 7, more or less. So imagine if you try to recognize a digit having only a 7 by 7 window, 7 by 7 pixels. So it's not easy. It's not easy to have global features when you have access to a very small area. The idea is that as we go deeper, we should have access, the filters should have access to bigger and bigger patches of the original image so that it can extract bigger and more complicated patterns. So let's continue with this. So as I explained before, not learning a spatial we cannot learn a spatial hierarchy of features when we have access only to a 7 by 7 initial input. So there is not enough high-level information for each of the final filters to extract. And also it's too big feature maps. So there are more than 500,000 parameters, which will eventually lead to overfitting. We have too many parameters to fit. And this is why we use max pooling. Now, there are other ways of downsampling. So one way would be, as I mentioned before, to use Stride 2 when running on the at the convolution layers. And another way would be to use a different pooling, for example, average pooling. Now, the maximal presence of different features is better than the average, first of all, regarding average pooling, because we are interested to see if there is in this area a specific feature or not. So taking the average will blur this feature, the existence of this feature. So this is why we use max pooling instead of average pooling. Now, another thing why we don't use strides is because if we use stride, we will have a sparser window of the inputs. And this is not good because we want dense information. And after we get this dense information, regarding the features, we want to see if the feature exists or not with the max pooling. And the idea is that we don't need the spatial information, we need the feature information, mostly for classification. Now, let's switch gears and see what else we can do with this convnet. This time we will build a model more or less similar to the previous one, but we will train it on a small, more realistic dataset. So we will use images of cats and dogs, a small dataset, so 5,000 in total pictures, 2,500 for dogs and 2,500 for cats, so balanced. And we will use only 2,000 of them for training, 1,000 for validation, and 2,000 for testing. So it's a very small dataset for this kind of data, for real images. And let's see what we can achieve using this. So here are the steps, what we are going to do if we have time. First of all, we will train something from scratch with no regularization. We will be around 70% accuracy, which will be the baseline of what we are trying to do here. Then we will introduce something to avoid overfitting, which is called data augmentation. We will see different techniques, and we will increase the accuracy to 80 to 85%, which is huge in comparison to the 70%. And then we will use some pre-trained networks in order to do one of the two things, either feature extraction, we will explain what this is, or fine-tuning. And using this, we will achieve something like 98% accuracy, which will be more or less the state of the art of what you could do back then with this Kaggle dataset. So the idea is that you have to download the data. Here I have already downloaded the data and pre-processed in order to have this, because the dataset is bigger. So I have the train, the validation, and the test splits already performed. So we will just load it. So the data are here and under this local directory, and you can see more or less what exists here. So under this cats versus dog small, we have three folders: the test, the train, and the validation. And under each one of them, for example, under train, we have two directories, the cat and the dog. And under the cat, we see that we have 1,000 images. Also under dog, we have 1,000 images, etc. So this is more or less the structure and what we are going to use. Remember more or less the structure because it's important on how we will read the data. So we have the train, test, validation, and under each one of them, we have the cat and the dog. And here are some examples of the images. So you can see that we have, again, real life images. We have different shapes, different sizes, different resolution, different backgrounds. So many things. It's not like the 100 images that was very specific. Now, let's build the model first of all. Again, from scratch. This time, we will include the pre-processing of rescaling inside the model, because this is actually something that we can do. So layers.rescaling, and this is what we multiply by the input tensor. So we will divide by 255. So we can feed directly the original data. And then we have these com2d and max pooling blocks. So we have all this. The idea is that we have for all of them activation ReLU and kernel size 3. And we start from 32 filters and we double every time. So this is a quite common pattern to double the size after a few convolution blocks. And between all these convolution layers, we have max pooling with pool size 2, which is again the default. We flatten in the end, we output 1. So for output, we have dense with sigmoid because we have a number either 0 or 1 as a target. So we want the output to be between 0 and 1. So let's build this one and continue. No, let's go back to plot the summary. So here is the summary. Again, more or less what I explained before. The input will be 180 by 180. It's just an arbitrary number. And then we will, this is just divide by 255. And at each layer, if it's com2d, subtract 2, and we have this number of filters. If it's max pooling, we divide by 2, more or less. So again, here, here, etc. In the end, we have 9 by 9 after the max pooling. The last convolution layer is 7 by 7. We have flatten and one output. Now, let's configure let's compile more or less model, binary cross entropy, nothing new here, RMS prop, and accuracy. So for the data preprocessing, first of all, we need to read the picture files. We need to decode it from JPEG to RGB file, the pixels, the 3 color channels. Then we're going to convert it to floating point tensors, so TensorFlow tensors, resize to 108 by 180, and then pack them to batches. Remember, we have to fit batches. In order to do all this, there are many ways to do this. One easy way is to use this image dataset from directory to read the images. And the idea behind this is that we have the directories. So let's see how we can actually use this. So we import it from TensorFlow Keras utils, and this is how we define them. So we will define 3 different datasets, train, validation, test. Each one will be the output of this function, the image dataset from directory. And here we have the dataset directory plus this. So this is the path of the directory that contains the images for the specific dataset. And we can define the image size. So if we want to reshape the image that are whatever shape to 180 by 180, we can define it here. And we can also define what is the batch size, because again, we fit batches. So we have the same parameters for all of them for these 3 different directories. Let's build this, and the output is how many files it found and how many classes. So we have 2 classes, cats and dogs, because there are 2 directories under each one of them. And we have 2000 train, 1000 validation, and 2000 for test. Now, the idea behind this, so this is one dataset object, a specific dataset object. And the idea is that TensorFlow.data.dataset is a very useful tool if you are training using Keras, because it's fast, it can handle asynchronous data prefetching. So it's optimized in order to parallelize the data prefetching. Let's see how this works. So we will see a dummy example to get familiar with this thing. Here we will use a NumPy array. We will create a random normal with 1000 by 16. So this is a number of samples, let's say, and this is the number of features. And we can build a dataset out of this data using the dataset.fromTensor slices. So if we have a NumPy tensor, we can use this, the same way we used before the images from directors. And we feed this NumPy array, and then this dataset is an iterable object, is an iterator, which means that we can use it inside for loops, or we can call next on it. So here we will take each element and we will print the shape of the element. And here you can see that we get only 1 sample per time. So we have 16, not even 1,16. So the idea is that this doesn't feed batches. We have to define it if we want it to feed batches. This just removes the first dimension, the first rank of the input tensor, because it assumes that it's the dimension for the samples, and it returns the rest of the ranks, the rest of the ranks of the tensor. So here only 16. But what we can do is that we can define the .batch with a number. So this will be a batched dataset. And here we can see that we have batches of 32 samples and whatever we have for each sample. More or less, this is how the previous dataset worked. And the good thing is that we can use the .map method in order to apply to each sample a specific transformation. And we can do it, for example, using lambda, like here, or we can pass the function itself. And here the idea is that, first of all, we use only TensorFlow operations, because this will be applied on the tensor flow tensors, not the NumPy tensors. And here we can say, for example, we want to reshape this. So the idea is that it's running on the fly for each one of these, and the output will be the reshaped after we have applied this. So dot map is quite useful if you want to apply specific things. Now, displaying the shapes of the data. So here we have the trained dataset, what we defined before for the images of cats and dogs, and we will get batches of data and labels. So we can see that we have 32 samples. Each image is 183 color channels, and we don't have dimension for because we have just numbers for the labels. Now, let's fit this model using datasets. So the idea is that you can run it. I will not run it right now because it takes some time. I have already run it and saved using the model checkpoint callback that we saw previous time here. So let's see, it's run. And now what we can do is that we can, okay, here I will import, I will wrote this part to import the history because we didn't have the history now. I already saved it. And the idea is that we just want to see, okay, how did this perform? And here we will plot the training and validation, both the accuracy and the loss. And what we can see from this is that we have too much overfitting. So you can clearly see that for the training, the accuracy is almost 1, the loss is almost 0, but it's not the case for the validation data. So for the validation data, even from epoch 6 or whatever this is, we start having something flat, we start having overfitting. So let's see what we can do for this. Now we have a convnet because we have convolution layers, but it's not there yet. Let's see what is the performance of this model. So for this model, we have something like 69.7%. Let's see what we can do for this. So around 70%, what we expected. The problem is overfitting. What we have already seen in order to avoid overfitting is dropout or L2 regularization. And now we will see another solution, which is data augmentation. And in combination with dropout, it can boost the results up to 80 to 85%. Let's see what is data augmentation and how we can use. First of all, there are many ways to use it. So the data augmentation, the idea is that we don't want the model to get the same image again and again, because it will just memorize the image. So it will know whenever we have these values for these pixels, the output will be this, no matter what is in the image. So what we want to do is change the values of the pixels, but still get the same idea, the same label. For example, if we have classification. So we have a dog, we still want to have a dog, but a slightly different image of this dog. So there are different ways to achieve this, and we will see some of them here. So what we will do here is that we will apply some random transformations, like flipping the image or rotating or resizing a bit the image, and we will do it using a sequential model. So let's see how we can do it. Again, there are many ways. Usually, for example, I do it at the sampler, at the data sampler, when I already have the NumPy arrays, but this is a good opportunity to see how you can do it using the layers that can achieve this. So in kernels.layers, you have some augmentation layer, image augmentation layers, like the random flip, where you can define if you flip horizontal, vertical, or both. You have the random rotation, what percentage will be the rotation, for example, plus minus 10%, like this one, or random zoom. So you can have like this one, 20% zoom in or zoom out. And if, of course, you zoom out, you have to pad somehow the rest of the pixels. There are different ways. So here, what we will do is that we will define a simple sequential model with these layers. And this will be the data augmentation model that we will use like a function, let's say. So let's see how this works. Here we will just take one image per iteration. We can use the .take method, and we will pass the images through this data augmentation model. And the output will be the augmented images. This time it will be tensors, TensorFlow tensors. So we have to call the .numpy and as type an integer 8 so that we can have the actual image. So for the same input, okay, I cannot scroll, just a second. So for the same image, you can see that we have different, no, I'm going to go back. So we have different augmentation that are either flipped or rotated or something like this. And this is the main idea for data augmentation. So let's use this in our model. The idea is that we will define a new model that includes this at the bottom. So again, we define an inputs layer with whatever we have here. And then we pass this inputs tensor through the data augmentation model. And we will take this output tensor. And then we can pass it to whatever we had before. So these layers are more or less with what we had before. The only difference is that we also have here a dropout layer. So we compile it, same as before. Again, two differences. One is that before the rescaling, we have this data augmentation, and we added this dropout. Now let's see how this model that we will train from scratch performs in comparison to the previous one. Again, you will not see the training. I already trained, etc. So we will just see the results. And here we will plot the results. So I will just load this JSON file with the history. And what we see here is that it's much better than before. So we don't have that heavy, how to say, that heavy overfitting as we had at the previous model. Also, one difference is that now we trained it for 100 epochs, so 3 times what we had before. And this is because we expected that the overfitting will hit much later. And you see it here that even here at epoch 40, it still doesn't overfit that much. It could be worse, okay? So this is more or less why we use data augmentation, not only for image data, for other kind of data too. For image data, it's very common, and also why dropout also helps. Now, let's see the results. So we have something like 82 from 70 point something, we went to 82, which is 69 point something, which is huge. I mean, it's really huge. If you have this kind of boost of more than 10%, it's very good. Usually we fight for something like 1-2% or something like this. And if you keep fine-tuning this kind of model and you play with how many layers and how many filters, and if you add this and that, you can achieve maybe up to 90%. Very difficult, but you could go up to 90%. But you cannot go above using only these 2,000 images. So it's quite difficult. And here is why we will leverage pre-trained models. So let's see how we can do this. And this is some more or less a pattern what we use not only for image, for computer vision, but other kind of data too, for example, for text. So common practice is when we have small data, then we use another model that is already trained at a similar task. It's important to be more or less similar, but on a much larger data set. For example, here we will use pre-trained models on ImageNet, and ImageNet, as I mentioned before, is a very popular dataset with more than 1.4 million images, more than, not more, 1,000 classes. So these classes include also dogs, different kinds of dogs and cats and other animals, objects. So it's everyday objects. So it's quite close, and this is quite similar task, and this is why we can use it. We will see two things. One is the feature extraction, and one is the fine tuning. So let's start with the feature extraction and explain what this is. So the idea with feature extraction is that we have this, where is my mouse? So this original model with the trained convolution base and the trained classifier. This is, for example, the 1000 dense layer. And what we will do is that we will remove this classifier and we will add a new classifier with what we want to classify. For example, dense with 1 and sigmoid. And this will be randomly initialized. We will freeze this part, and this is why we will use this as feature extractor, and we will train only this. So let's see how this will play. We will use VGG16, a quite popular old model. We have much better models right now, but the idea is that VGG16, the structure is more or less similar to what we have seen now. So convolution layers and max pooling layers, more or less blocks of them. We will see the structure action now. So the idea is that we define, first of all, under keras.applications, there are many pre-trained models. We will call the VGG16. We define the weights to be from ImageNet because we want these pre-trained weights. We don't want to include the top classifier, the 1000 classes. We will remove it, so false, and the input shape will be what we have already defined for the sampler, for the generator. Let's see the structure. So as I mentioned before, some convolution layers and max pooling, convolution, max pooling, etc. And the idea again is we start with something as filter, for example, 64, and we double it more or less after a few blocks. So double, double, double. And the final output of this will be 5 by 5 by 512. So we want to take this and then we will flatten it, etc. So there are two approaches for this. One approach would be to prefetch, to run the conv base over all the data, save the outputs as an NumPy array, and then run the classifier, train the classifier on this, which is the fastest. We just take the results one, we run the conv base once, and then we train many epochs the classifier. But this doesn't support the augmentation. We want to have different images at each epoch. So the second way that we will see is to extend this by adding the dense layer on top, which is slower, but we can use the data augmentation. So let's start with the first one. We just apply fast feature extraction without data augmentation. So what we will do is that we will use this function on dataset, an empty list for the features and the labels, and for each image and label batches, we will pre-process. So again, each model from this pre-trained have a specific way of pre-processing the data. Some want from 0 to 1, some want from -1 to 1, or mean standard deviation, normalization, whatever. The idea is that since you don't know it, you don't have to know, there is already under Keras applications and whatever module you need to use this pre-process input. And this, you can use this in order to get the pre-processed images the way the specific model needs it. So here you feed just the unsigned integer from 0 to 255, 3 channels, and whatever it needs, it will be applied here. And we take these pre-processed images, we pass them through conv base. Be careful here, we use predict so that we get a NumPy array as an output. The same way, this is a NumPy array. And we append to the list the results. In the end, we just concatenate them. So this should be quite fast. We run it on train, validation, and test data. Not so fast. Should be completed by now. Yeah, it's completed. So now we have these features, and we will run the classifier on these features. So let's see what it looks like. So we have 2000 for the train features by 5 by 5 by 512. And remember, this is the output of this conv base layer. So let's define the classifier. So the classifier is just, we take this as input or the input shape. We flatten it. We will use this 256 layer for how to say the embedding of these features, and we will apply some dropout, and then we will have the usual sigmoid with one output dense layer. Nothing new here. We will again use this, and we can train this. This will be fast. I can train this here. So let's see, training, it goes quite good. And let's see the plotting results. So, what happens here? Let's plot the results. So we have again train, validation, both the accuracy and the loss. And well, it's not bad. I mean, we have an accuracy of more than 97%, almost 98%. We do have some overfitting, of course, but the idea is that it's quite good. So let's see what are the final results on the test set. I don't have it here. Yeah, I guess. So it was around 97% what we can achieve with this. But we do have overfitting. So let's see what we can do if we use data augmentation to avoid the overfitting part. So the idea here is that we will use the same thing as before, but we will freeze the weights. So we create the same model, but we call conv_base.trainable false, and this will have not trainable weights. And we can see it here. So if we switch it to true, we have 26 layers that have weights, trainable weights. If we switch it to false, it will be 0. So this is what we did. We switched it to false. Now, let's build the model. So same as before, we write this sequential model with the augmentation. We create the input, we pass it first through the data augmentation, then through the preprocess VGG preprocess input, we take this symbolic tensor. We can use it also this way. Then we pass this through the conv base. We flatten, dense, drop out, and dense again. So this part is what we saw before. And we build the model, we compile it, and we train it. Again, I will not train it here. We have already trained it. And here are the results. So the idea here, as you can see, is that it's much, much, much better than before. We don't have this, this overfitting that we saw at the previous curves. Here, it doesn't overfit almost at all. We could, of course, continue training. It will not get much better. But we have achieved some small, maybe 0.5% better accuracy. So let's see the results. And we have 97.65 actually, which is good, which is pretty good. We gain something like 0.5%. Again, when we are more than 97, this 0.5 is important. Now, these were the two ways to use a pre-trained model as feature extractor. So we don't train the model itself, we just use the model either with data augmentation or without, and we train only the classifier. The other way would be to train also the model itself, the convolution model, either the whole of it or part of it. So here are the steps of what we are going to do. First of all, we will add our custom network on top of the already trained base network, which is something that we already did before. So we take the conv base and we add it on top of the pre-train of the custom model on top of the conv base. Then we will freeze this base network. We already did it with trainable equal false. Then we will train the part that we added, so the classifier part with the two dense layers. We already did this. And the next steps is to unfreeze some of the layers and jointly train both the unfrozen layers and the classifier. So this is the VGG network. And what we are going to do is that, so this is the original one. Here is the part that we added and we trained. And what we are going to do is that we will take these layers and we will fine tune this. Now, be careful when we turn to trainable, we have to pay attention. It's not the case here, but in other cases, not to to turn to trainable the batch normalization layers because they behave quite strange. So let's see the summary. Here is the summary of what I saw before. And what we want is this block 5 to unfreeze these ones. So we freeze everything and we unfreeze 1, 2, 3, 4 from the top. So let's do this. We turn everything, actually we do the opposite, we turn everything to trainable and we turn the trainable of all but the last 4 to false. This is another way to do it. And we want to fine tune now the whole model with the classifier. So we will compile again because we will use a much lower learning rate than before because we don't want to break things too much in the block B. Again, I have already trained it and let's see the results. So 97.8. Actually, if you run it yourself, sometimes it will reach 98 or even 98.5. So this way, the fine tuning can get maybe the best results, of course, given the data set that you have. And these are actually very good results. I mean, at the original data set in Kaggle, when it was introduced, this data set, this would be at the top 10 results. Of course, we cheated because we used a pre-trained network, but on the other hand, we trained on just 1/10 of the data. So the total data set had some 20,000 images, we just used 2,000. So we cheat back. This was more or less the introduction to computer vision with deep learning. We just saw a classification problem with different ways. So we saw the architectures, how we can use data augmentation. Again, convnets are currently the best type of machine learning models for computer vision tasks. I mean, there are the transformers, but they are not there yet, especially for specific kind of tasks for computer vision. It's possible to train one from scratch, and we see that we can get quite decent results, even at a small data set. And regarding the convnet, the layers, what we saw is that they learn a hierarchy of modular patterns and concepts to represent the visual world. And again, the idea is that we start from very simple patterns and then the next deeper kernels learn how to combine them to more complex ones. Also, data augmentation, we saw that we can counter overfit quite a lot when using also with dropout. And regarding pre-trained convnets, we saw 2 quite easy ways to use them, either freeze it and use it as a feature extraction or fine-tune part of it. So this was more or less for this session. Thank you very much.